Hello, today I'm going to present you a video on proximal policy optimization or PPO. My intention is to highlight the key component of the PPO and provide some guideline for future development. Okay, let's start. Here you see the first part of the code. In PyTorch, you import the necessary library, and here is related to the GPU using. We have to create an environment for every reinforcement learning scenario that we develop. Here, environment is simply created with one line of code. In practice, you have to develop a custom environment that maybe more than 500 line of code, maybe 200 line of code. You have to develop a realistic environment that resembles that reality. This is very important component, and I can say the most critical component of any reinforcement learning code. We have also the code associated with the agent based on the neural network. I will back and explain this part again. Another component is related to the plotting the output. So we have to generate the output and generate some plots. Another key component is generalized advantage estimate or GAE. This is also integral part of any code that we develop using PPO. We have a optimizer that is the brain of any PPO code. We do optimization and conduct training. I will explain this. And finally, we have to initialize some hyperparameter and develop the main body of the code. Here you see some hyperparameter are initialized. The first one is hidden size. The value is 256. Um, Learning rate. I would suggest using a smaller learning rate. Number of steps. Mini batch size is 5. This is a very key hyperparameter for PPO. I would suggest to carefully tune this hyperparameter, and we have number of epoch. This is also key to PPO. We define a model, actor critic model. We specify number of input, number of output, and hidden size. Or we define our optimizer, which in the most of code is Adam optimizer. We pass the final learning rate to it. We define the maximum number of the frame or number of the maximum number of episode, which is here is 15,000. But this is too much. I would suggest using 3,000 episodes is enough in most of scenario. And here, okay, is the main body of the code. Um, we create some list, one list for luck probability. In PPO, we model the policy using luck probability. We create one list for value, one for state, one for action, and one for reward, and also initialize entropy to 0. Okay. For a specified number of the step, we repeat the following operation that you can see here. Okay, we first start with the initial state, pass to the model. The model generates two output, value, critic output, and distribution, actor output. We sample distribution to generate our action, and we implement the action in environment to calculate the reward and compute the next state. As you remember, I said to you, we have to develop a custom environment. When you develop your own code, you just call the developed environment and pass this action to that environment. Okay, and we have the log probability, and the way we compute, you can see here, we have entropy, and the way we compute it. And for each step, we add the output to the created list, log probability, value, reward, state, and action. Okay, we repeat this operation for a specific number of the time until our list becomes full of data, and then we pass this data to the optimizer to do optimization. If you remember, in DeepQ network code, we had to execute action, do optimization, execute action, do optimization, but we don't see this trend here. We sequentially execute the action, collect the associated data, and store in the list, and then use this data to do the optimization. And we call the PPO unpolicy algorithm because the PPO use data associated with current round of the operation. You can see we created the list, we fill the list, and we do optimization. When we back again, we recreate the list and we have to generate new data. And always we use data associated with current round of operation. Okay, after this, we call the generalized advantage estimate and pass some value, next value, reward, and value to compute the return. Okay, you can see this function here. Generalized advantage estimate, it receives next value, reward value, and we have two critical hyperparameter that I recommend this value for developing your code. And based on the idea of the generalized advantage estimate, this part has been written. You can check the associate paper and find it in Google Scholar. This part is very critical for the correct operation of the PPO, and I recommend you to use this part for your code. This is the correct development, but before that, try to fully understand it, what is happening. Okay, then we after we compute the return, we need to convert our list data to tensor data. You see, we convert our data to the tensor data, and we compute the advantage. Using this computed return, we subtract it from the critical output and compute the advantage, and finally pass all of them to the optimizer. Okay, now let's go and see what is happening in the optimizer. In optimizer, we use C2 function, PPO iter and PPO update. The objective of this PPO iter that is called here is to shape the mini batch for the rest of operation. The key is this random function, ran it function. Let's explain by example. Suppose the batch size is 40 and mini batch size is 5. It means this line of code means that it generates 5 random number between 0 and 40 and store in the rand id variable, and we then pass this variable to the state action log probability to shape the mini batch. And okay, now let's talk about PPO update. We shape the mini batch. We receive the mini batch as a input to the optimization step. We compute entropy, we compute the new log probability, and we compute the ratio of the new log probability to the old log probability, and we clip this ratio to bound it between a specific boundary. Okay. And finally, based on these two components, sur1 and sur2, we compute actual loss, and we compute the critic loss based on the return, and you can see here return and the output of the critic. And the final objective is critic loss, actor loss, and entropy. We plus critic loss with actor loss and subtract with entropy. Also, pay attention to these two value, please. Finally, we make gradient zero, compute loss function, and update the value. Okay, this is about the optimizer. This implementation is very standard and good written. You can utilize it for developing your own code. And you can use the same PPO iter function. Also, you can make it custom and use a different way to shape the mini batch. Okay, and the central to any deep reinforcement learning algorithm and PPO is the actor critic model. We have a critic part, we have an actor part. I am sure all of you are familiar with this part. And we have a forward function. We pass the input to critic and actor and compute two output. And then using actor output, we compute the standard deviation, and then we pass the standard deviation and actor output to the normal distribution to shape our distribution. And finally, we return the distribution and the critic output to the main code. Okay. I will share the link to this code in my Telegram channel. The ID is the same as my YouTube ID. Thank you very much.